Hi everyone, this is Mrs. J, and today we're going to be modeling with trig functions. Okay, so using our trig functions, specifically sine and cosine, is actually really useful for us in terms of real life scenarios because many things in life are cyclical and kind of have that wave shape pattern like sine and cosine. So we're going to look at a few different examples of just real life scenarios that kind of follow that sine or cosine wave shape. So let's look at this first one. Here it says the motion of a point on the outer edge of a riverboat's paddle wheel is modeled by this function. H of t equals 8 times the sine of pi over 2t minus pi over 2 plus 6. It's a mouthful. Where h is the height in feet measured from the water line, and t is the time in seconds the boat has mid-moving. So how high above the water line does the point go, and how far below the water line does the point go? So just to kind of visualize what's happening here, here's like a water line, and we have a boat, and it's like a big paddle wheel. So it has like all these little pedals that when it moves, it propels itself through the water. So in terms of what our axes represent, right, this represents the height in terms of time, so how far above, and this is when the height is 0, is at the water line. And of course, if it's a negative height, then it's just below the water line. And then this is our time that has gone by in seconds. So here we're actually given the function, so our job is to interpret what this function means. So first thing to notice is that we will want to first factor out that b value. So we'll rewrite it as pi over 2 times t minus 1 plus 6. So a few things they're asking. How high above the water line does the point go? So here they're essentially asking for a maximum. They want to know what is the maximum. And then they're also asking how far below does the point on the wheel go. So here they're asking for a minimum. And then how long does it take for the paddle wheel to make one full revolution? Here we can interpret that as them just essentially asking what is the period. So by looking at our graph, we can see that our midline is at 6 and our amplitude is 8. So that means that the distance to the maximum would be our midline, which is 6, plus 8, so the maximum value is 14 and height is measured in feet. So the highest that it goes is 14 feet, so it's right up here. And then again, to see the lowest it goes, which would be our minimum value, again we can start at our midline and we can subtract 8, and then we get negative 2, so we could say 2 feet below the water line. And maybe here I'll add above the water line to our answer. Again, I don't really want to give a negative answer for this one because it's asking how far below the water line does it go. So if it goes down to a minimum of negative 2, that just means 2 feet below the water line. And last, let's see how long it takes for our paddle wheel to make one full revolution. So again, if we interpret that, they're essentially just asking us to find the period. So here we can see our b value is pi over 2, which means we have a horizontal shrink by a factor of 2 over pi, which gives us a value of 4. So that means it must take 4 seconds, which is the unit of our x-axis, per cycle. So there you go. So sometimes we are given the model of something that is cyclical, like the height of something that's turning around, right? Anything that's on a wheel or a circle, its height can be modeled with a sine or cosine graph. All right, let's try another one. So here this says, consider a Ferris wheel that has a diameter of 140 feet. The lowest point on the Ferris wheel is 10 feet off the ground, and it takes 7 minutes to complete one full revolution. So just to kind of visualize what's happening here, right? We know that like the actual Ferris wheel, it's kind of lifted above the ground because all the little seats, they should not touch the ground as they go by. So it's always kind of like propped up with something like this. So we know this distance here is 10 feet. And we know that the diameter of our Ferris wheel is 140 feet. So we can kind of do a little math and we say like the maximum value up here, this is 150 feet in the air. And again, this is at 10 feet. So it says the lowest point on the Ferris wheel is 10 feet. We have that. And it takes 7 minutes to complete one full revolution. We can use that to help us when we create our function. So it says create a function, h of t, that models the height in feet of a point on the Ferris wheel after t minutes. Assume the point is starting at the lowest possible point. So this is when t equals 0. So actually, if we were to draw in, an x-axis, it would look like this, an x and y-axis. Okay, so first, let's talk about which function we should use. So if we're starting down at the minimum, again, we're starting down at the minimum, I think the best function for us to use would be a cosine function. So there's a few different things that we need to know. First, we need to figure out what our period is. So our period is 7. It says it takes 7 minutes to complete one full revolution. So we know that we need to find that b value for our function. So we would do 2 pi times 1 over b equals 7, and then we want to solve for b. So our b value is actually going to be 2 pi over 7. Kind of a strange b value, but that's okay. And then we will need to find our midline and our amplitude to help us complete this function. So we know the midline will be exactly halfway between the bottom of our Ferris wheel and the top of the Ferris wheel. So it's going to be at 70 feet from here, from the bottom. So we're going to cut this in half, and then we're going to add it to 10. So from here to here is 70 feet. But again, we started 10 feet off the ground, so our midline is actually at 80 feet, which means our graph is going to be shifted up 80, and then the distance from the midline to the maximum or minimum is 70, so our amplitude is 70. So far, here's what we have. So we have 70 times the cosine of 2 pi over 7 t plus 80. Now there's one last thing to consider. Since it says assume the point is starting at the lowest possible point, we know that cosine usually starts at the maximum, so we are actually going to need to reflect it. So our function should look like this. So now that we have our function, we can then use our model to determine the height of the point after 5 minutes. So all we would have to do here is find h of 5. And this is actually just something you could plug into your calculator. One thing to point out here, because of how we adjusted our period, this is actually in radians. Again, because we're adjusting from the period of 2 pi. So again, we need to make sure that our calculator is in radians when we're plugging in h of 5. So take a moment and do that in your calculator. And you should get about 95.58 feet if you round it to nearest hundredths. All right, let's try another one together. So this one says the hours of daylight in Seattle oscillate from a low of 8.5 hours in January to a high of 16 hours in July. So we know, throughout the year, as the seasons change, the length of the days changes. So again, it's a low of 8.5 hours in January to a high of 16 hours in July. How many hours of daylight will Seattle have in June? And we know that this could be modeled with a sine or cosine graph because this is cyclical. Every year it's going to go through that same pattern of how many hours of daylight we see, from a low to a high in the middle of the summer, and then back down to a low by the time we end up back in the middle of winter. So first we need to maybe try to visualize what's happening here. So I'll set up our axis. So we're going to, it says how many hours of daylight will Seattle have in June. So let's have our x-axis represent months that have gone by, and let's have our y-axis represent how many hours of daylight we have. So we know in January, that's our low. So let's call 0 January. And maybe we'll do like this time in months. So let's call t equals 0 January. So in January, there are 8.5 hours of daylight. And then, so if t equals 0 is January, then we have February, March, April, May. Here's June. June is when we reach, July, one more tick mark. July is when we reach a maximum here of 16 hours of daylight. So here to here. Okay, so I'm just going to mark this July so we remember when that is. Okay, so you can see that since we're going from a minimum to a maximum, this is going to be half of our period, so we're going to look like this. And then we know that after that, it's going to start decreasing again until we return to our low back in January again. So we know that our period is going to be 12. Remember, we're scaled by months, so of course it will take one full year to return back to the minimum. And then we can find our midpoint or our midline, which will help us also find our amplitude. So we can see here, this would be our midline. So it's going to be exactly halfway between 16 and 8.5. So that is going to occur at 12.25 hours of daylight. So this midline will help us determine that vertical shift that we need to do. So I'll write that down. And we know that amplitude is the distance from the midline to the maximum or minimum. So in this case, our amplitude is going to be 3.75. Before we can start plugging this all in, one other thing to consider is, well, the period is 12, but what's our b value? So we know it's going to be 2 pi times 1 over b. Our stretch or shrink factor should equal 12. So b is going to equal pi over 6 if we, again, multiply by b and divide by 12. So here's our b value. This is going to be our k value. This is going to be our a value. And again, here, since we're starting at the minimum, we should use cosine and we should reflect it. So here we can say negative 3.75 times the cosine of pi over 6t plus 12.25. So this would model the number of hours of daylight, or maybe I'll change it from f of x to h. Sorry, I should have said h of t. Erase this. H of t. So hours of daylight in t months since January. So it's important to remember that t equals 0 is January. So February is actually when t equals 1. So t represents months since January. I can be even more specific here. So now that we have the model, we can answer the question. How many hours of daylight will Seattle have in June and then in October? So June is going to be right here. So June is actually when t equals 5. So we would find h of 5, and again, we're going to plug this into our calculator to get a decimal approximation, and we do need to make sure, again, that our calculator is in radians. So if you plug that in, and we can round to the nearest hundreds, we actually get 15.50 hours in June. And then to find October, so remember every month is, we actually use the t value before the actual month. So for October, we would actually do h of 9. And again, we'll plug that into our calculator, just making sure that we are in radians. And we should get 12.25 hours, which actually makes sense because when it's 9, it's back to our midline. We actually didn't even need to plug that into our calculator if I took a moment to think a little more about it. But we know that every 3 months we're going to move from either a minimum to a midline or to a maximum or back to a midline. So we are actually right back on the midline in October. So there we go. So you can see how, again, anything that is cyclical, so I think weather is a very common one, or hours of daylight can be a really common one. Anything that's moving on a circle or like a wheel will definitely be modeled with sine or cosine. If we can make the model, then we can answer additional questions or make predictions about future values. All right, I have this last one for you to try on your own. So please pause the video and give it a try. All right, go ahead and check your work here. So the midline for this function will be at 39 inches above the ground, which is exactly halfway between 3 and 75, which means our amplitude is 36, which is the distance from that midline to the max or min. And then if it says that it makes 2 revolutions per second, that means that it makes 1 revolution in a half a second. So that's the length of a period. So if a period is 1/2, we could say 2 pi times 1 over b equals half. So our b value must be 4 pi, again, to create the period of 1/2. And then lastly, since it says assume that t equals 0 at the lowest point, so we will use cosine and we can reflect it so to make sure we're starting at that lowest point. So here's what our function would look like. Okay, that is all for today's video. Thank you so much for watching.